this was. Can you hear me? Can you hear me? Can you hear me? Am I audible? Can you hear me? Okay. So this is where we stopped. That for dielectric materials, D equal to epsilon naught E, where epsilon r was 1 plus chi e, where chi e is called electric susceptibility. Okay. So with that in mind, let us do something else. Constitutive properties of materials. We will do only the EM properties of materials. There are three. We are concerned with only three. First one is epsilon r, second one is mu r, and third one is sigma. What is epsilon r? It is the negative permittivity. Second is mu r, that is relative permeability. And what is sigma? What is sigma?
Surface charge density.
Yes, that is true. That is true, surface charge density. But it has a more popular sigma.
The damping factor.
No. Think about electrical things. Not that. Remember this. What is sigma?
Mobility.
Couldn't get it fine.
Mobility.
No. It has units of Siemens per meter. Sigma has units of Siemens per meter. Conductivity. Okay. And in this class, we will exclusively concentrate on linear, homogeneous, and isotropic materials. Now the question you ask ourselves is, what are these things called linear? First, linear means that epsilon r, mu r, and sigma, they are not functions of E. What I mean is, no matter how big or how small our E or H is, ER, mu r, and sigma, they do not change. Okay? Understand? Had this not been the case, had mu r and epsilon and sigma would have been functions of E and H, we would have to write epsilon r was epsilon r for a given E and H. But that is not the case. Epsilon r, mu r, and sigma, they remain constant no matter how big or how small field we are. So a linear concept is okay. It's a linear concept. Okay. What is homogeneous? Homogeneous means that if I take a material, a cube of some dielectric material or something else, the value of mu r, epsilon r, and sigma, they are same everywhere in the cube. It's not that here it has some mu r, here it has some other mu r. It's not that. The entire cube is made up of exactly the same material, and it has the exact same value of the constitutive properties. That is the mu r, epsilon r, and sigma. Is it okay? In practice, no material can be truly homogeneous, but we assume that it is homogeneous for our case. Is it okay?
Sir.
What is isotropic? Isotropic means that these things, they are not functions of direction of the field. What I mean is, we can simply write D equal to this. No problem. Had this not been isotropic, we had to write it in this way for unnecessary dx, dy, dz. That is equal to better write. You have to write it in this way, dx in a matrix form. In this form. Or in other words, dx would have been epsilon xx dx plus xy ey plus epsilon xz ez. Here, okay, something like this has been much complicated. And this is called permittivity tensor. This is a tensor quantity. It's neither a scalar nor a vector. Okay, this is called a tensor quantity. But we don't have to worry about that. We can simply write dx equal to epsilon dx, sorry, dy epsilon dz epsilon ez. Okay, and dx is independent of ey and ez, dy is independent of ex and ez, and dz is independent of x and y. Is it okay? Isotropic and anisotropic concept. There are a few anisotropic concepts which have great application in microwave engineering, suppose ferrites, but for this course we are not going. So these are okay, linear, isotropic, and homogeneous. What is meant by
Yes, sir.
okay. Another thing is called non-dispersive. Non-dispersive means these things are independent of frequency. That's it. We will not change it. Okay. So I think with this we come to end of our electrostatic discussion. Any doubts regarding electrostatics?
Sir, can you repeat the non-dispersive part?
Non-dispersive means that these things, epsilon, mu, and sigma, they are independent of frequency. Had they been dispersive, they would have been functional. But we assume it's non-dispersive. We can simply write D equal to
Independent of
frequency.
independent.
Frequency.
Okay.
Okay. But this, that is not hard, very commonly used. This linear, homogeneous, and this isotropic, they are used. We assume it is isotropic, linear for this course. Okay. Any other doubts? Any other questions? Or we can move to the next very important topic. Oh, just one last thing. Suppose I have a cylinder. Okay, the cylinder has got charged particles, and some current I is flowing out of the cylinder, not necessarily from this end, it will flow from anywhere. Some current I is flowing from anywhere, from all possible directions. Rarely doesn't happen, but think in this way. Okay, some current I is flowing. Obviously, if current is flowing, the charge in it must decrease with time due to the conservation of charge. So can we write this I equal to minus dq by dt? Can we write this? Current is flowing out of the cylinder. Obviously, due to conservation of charge, charge is flowing out, so charge will decrease with respect to time. So I equal to minus dq by dt. Now, what is I? Since current is flowing all over J ds. J is the current density. You probably know. So this is 1. If the charge density, volume charge density of the conductor is rho v, then Q will be equal to volume integral of rho v dV. Is it fine? Is it okay? So
The cylinder was already charged.
yes, it's charged or it contains some charge. Just assume like that. Hypothetically, it has some charge in
Okay.
it which is flowing out of it. Somehow. J ds, that is equal to minus d dt of q dv. Fine. But from divergence theorem, what do we know? That volume integral of divergence of J dV, that is equal to surface integral, post surface integral of J ds. So volume integral of J dV, that is minus d dt of q dv, or sorry, is it okay? Is it okay? We have just replaced this. We started here. We started here I equal to dq dt, but I is equal to closed integral of J ds. Had we have assumed that it is through only one surface, then okay. Now q equal to v OV dv, or q total charge equal to the volume density into integrate over the volume. So we have simply we can take this. Now we have used divergence theorem to get this result. This result is called the equation of continuity. Divergence of J, that is equal to minus del T by U. Because as the current is moving out, the charge inside the conductor is it okay? What would have happened if I taken a current line like this? It is considered like this. A resistor R. Okay. It's a wire. And what will happen if I apply equation of continuity here? What will happen here? I equal to what?
So will we get 0?
We will get 0. Why? Because J is in this direction, J is in this direction, but N is in this direction. They will cancel. Here, the charges are entering, same amount of charges entering and leaving the conductor. So, J is not 0, by the way. J is
Yep. Yes,
not
sir.
0, but this is 0. You understand the difference? J is not 0. Definitely current is flowing, but this integral must be 0. Because current is flowing only through this rails, and here N is top, N is opposite. Okay, this is that. Anyway, finally, so we move on to the next topic, that is the steady magnetic. Steady magnetic field, or magnetic field produced by currents which do not vary with time. Magnetic fields produced by currents which vary with time will do it. For the time being, we assume that we only DC current is flowing and the current does not change with time. As a result, the magnetic field also does not change. So, what is the first law which comes to mind when we discuss magnetic fields?
Biot-Savart law.
Biot-Savart's law. What does it say? If I take a wire which connects I, okay. Once again, we assume I is constant with time. I can change it. So I take a very small element, set here, and we would like to measure the magnetic field at a distance p. Let us say this vector is r, then dh equal 1 by 4 pi I dm cross r times mod r cube equal to 4 pi I dl r mod r square, where r small, this is a unique vector in the direction of r. Is it okay? This is from, I think you have studied in, I think sure you have studied this in your class 12. This is okay? This is Biot-Savart law. What does it state? What does this
Yes,
mean?
sir.
What does this mean? Our direction of H? H is perpendicular to both dl and r, because it has a cross product. H is a vector because cross product of two vectors is a vector, and it is perpendicular to both dl and r. Is it okay? Is it okay? Let us solve some problems. I have got an infinitely long straight wire along z direction. Okay, the current I is flowing. Current is this I. It is flowing along plus z direction. Okay? This is my coordinate axis. This is my z. This is my x. This is my y. What is the value of magnetic field at this position P? Whose coordinate 0. How to find it? This can be solved very easily using Ampere's law, but for the time being, let us focus ourselves on Biot-Savart. How to find it? And what does Biot-Savart law say? Biot-Savart law says that dH. Let us take a very small element here. Let us take a very small element here. Okay. Whose is Z? Just 1 second. A small element Z, okay, of length dz, and the distance of that small element from the x origin is z. So this is this vector. What is this vector? What will be the r vector? R vector will be what coordinate system we should be using? What coordinate system we should be using?
Cylindrical.
Cylindrical. So what is the coordinates of P in cylindrical coordinate system? Rho 0. And this dz, it has the coordinates of 0, 0, z. So r vector would be rho a rho minus z. Okay. So as per Biot-Savart law, h dh equal to 1 by 4 pi I dz cross r by r square, or I by 4 pi dz cross r. Dz is equal to dz az cross rho a rho minus z az times r square. Now what is az cross a rho? Is simple. It is in this order: a rho, a phi, az. A rho cross a phi is az. A phi cross az is equal to a rho, and az cross a rho is a phi. So this is a phi. And what is az cross az? What is az cross az?
0.
0. So this would be I by 4 pi dz rho dz by r square. Okay. Oh, there will be I forgot to put dz plus this will be r cube, because this is r. Okay. We took r, so this will be r cube. Not r square. So this is I by 4 pi rho dz. What is r cube? R cube will be rho square plus z square to the power 3 by 2. So what is h? And the reaction will be a phi. What is h? H is I by 4 pi a phi integral of minus infinity to infinity rho dz rho square plus z square to the power 3 by 2, as the wire was infinitely long. Now for our convenience, we take z equal to rho tan theta. So dz would be rho sec square theta d theta. So our new integral becomes a rho is new integral becomes h equal to, oh, I have already I by I a by 4 pi pi by 2 minus pi by 2 rho square sec square theta d theta by rho cube sec cube theta. So sec square theta and sec cube theta gets cancelled. 1 by sec theta divided, that is cos theta. So that is equal to I by 4 pi rho a phi minus pi by 2 pi by cos theta d theta. This integral is 2. You can check. That is I a rho by 2 pi. Sorry, I a phi by 2 pi. So h is in phi direction. H is in phi direction, and this value is given as h vector. H is given as I by 2 pi rho, which means this is my wire and this is my rho, and this is in the phi direction. It is both perpendicular to R and Z. Is this okay? I am doing the showing the repetition to you again for your convenience. We started here, right? Our rho was rho 0 0, because this was our rho. Rho is pointing outwards. Rho 0 0, and dz was 0 0 z. Therefore, R would have been the final point minus initial point. So rho A rho minus Z is. So what is R? So what is mod R square? Rho square plus Z square. And what is R? That is R by R. That is rho A rho minus Z is Z. Rho square plus Z square. So we just put this here and use the result that Az cross rho is A5, Az cross Az is 0. Now we carry on. So only 5 component will be there, and we have just integrated the answer. The answer is this. Had we had used Ampere's circuital law, we would have got this answer much easily. But for now, we are focusing on the Biot-Savart law. Ampere's law will be more. Any questions?
Sir, can you scroll up a bit?
Yes, I can. Here, here.
Sir, a bit farther.
Okay. We started this one.
Here.
Hello, sir.
Yes, tell me.
Sir, in the graph, the row value is 0, row 0. P
Oh,
value.
this is in. Okay, this is in Cartesian, and this is in. Yes.
Okay, sir.
Okay. Next class we will do Ampere's law, then probably vector potential, then we will go to the time manifolds. Is it okay? Just one last passing comment. What is this? We will see this next class. This next class. What is this? What was this? What was this?
Flux. Electric flux.
No, that is not electric flux. Electric flux is this. This was an electric flux to a surface. But it may not be close to all this. But this is it. This is not it. What is this value?
Rho V by epsilon naught.
Rho V by epsilon naught. Right, absolutely correct. This is not zero because the electric field lines, they originate from a positive charge and terminate from a negative charge. Okay. What about the magnetic field lines?
0.
Do they originate anyone or where do they terminate?
Will
Since
that
we
0?
see exactly, since we do not have any magnetic monopole so far, no magnetic monopole has been reported anywhere in the world so far. So we simply write this to be 0 because the field lines will not originate from anywhere and is not terminate. This is called the Gauss law of magnetism. Also, it can be written as this. Okay, what is the difference between this and this? What is the difference? This you probably know. What's this?
H is the horizontal component.
And B, this is only for free space. What is the difference between this and this? Can anyone tell me? What is the unit of this? What is the unit of this? What we just calculated? H equal to I A psi by 2 pi u. Now can you tell me what is the unit of H? What is the unit of H? What is the unit of I? What is the unit of I?
Ampere.
Amperes. What is the unit of A psi? A phi? What? A phi, what is the unit? No unit. What is the unit of 2 pi? What is the unit of 2 pi?
No unit.
Hmm? Sorry?
No unit.
No units. What is the unit of rho? What is the unit of rho? Rho is what? This distance. So what will be the unit of rho? What will be the unit of rho?
Ampere per meter.
Meter.
Meters. So H will be amperes per meter. H is amperes per meter. What is the unit of B? He is named after a scientist. Very, very famous scientist. Has a lot.
Weber.
No. It is Weber per
Tesla.
meter square. It is Weber per meter
Yes.
square. But it's named after another scientist.
Tesla.
Tesla. It is either Weber per meter square or it is called Tesla. So the units are different. So they cannot be the same. So what is H and what is B? The difference between B and H. Clearly they have different units, so they cannot be same. What is the difference between B and H? Can you tell me?
That B is magnetic induction.
Not induction. And what do you mean by magnetic induction?
Magnetic field in unit area.
Magnetic field in unit area. And then what is magnetic field? B. H is called the magnetic field intensity. Okay. This unit as we just said is called as amperes per meter. This B is called
Magnetic flux density.
absolutely right. So why didn't tell me when you know the answer? Magnetic flux density. Its unit is both are very popular. Some people write Weber per meter square, some people write Tesla Weber per meter. And magnetic flux is phi, which we see later when we discuss electron induction in great details. Its unit is there. Okay. And B and H is written by B equal to free space at least B equal to mu naught H. Even in good conductors, except in non-magnetic materials, in dielectrics, even in good conductor like copper or silver, which doesn't any material which is not attracted by a magnet, this equation holds. For some magnetic materials, this is not true. We have to write this. For magnetic materials, this is not mu naught H. But for everything else, this is B equal to H. What is mu naught? Mu naught is called permeability of free space. What is the unit? What is the unit? What is the unit of mu naught? Henry square. Okay. Okay. So revise the exercises, try problems anywhere you can start. You can WhatsApp me or call me. Okay then. See you on Thursday for Group B and on Friday for Group C. Thank you very much.